So welcome to lecture 15, and we'll wrap up the discussion of energy. So as you saw in the last video, energy is a very useful approach to there's the energy approach and force approach of doing things, and they both have its pros and cons. In the main pro for energy is really if you can do it, it's usually easier, right? But there are some problems where the energy approach is not easily doable, and if it's not, the force approach with the kinematics equation, etc., will be your approach. Now, traditionally, as we saw, right, traditionally energy is kind of defined as the ability to do work. So what is work done? And the warning I give you is try to think of work not as the everyday life meaning of work, but it's a specific jargon. It means something specific, right? It means this. So the work done, it's always on something by something. So on something by a force. Okay, it's defined as the amount of force applied over a distance. And the algebraic version in equation form is this, and it requires a dot product, okay, and an integral, okay? But there are certain simple cases which this will simplify. However, we're basically going to talk about that today. However, you see that I have proved last time that the change in kinetic energy is equals to basically this combination. So this is called the work energy theorem, because the amount of work a force does on something basically changes the kinetic energy. So I find there is a better way to define energy because of the work energy theorem. Work is the same thing as changing kinetic energy, so might as well just say it's the ability to change an object's kinetic energy, okay, or change its velocity essentially, because kinetic energy is the energy due to motion, due to velocity or speed, I should say, right? So so energy is a measure of how much you're able to change that. And for example, if you have gravitational potential energy is mgh, and so that is the amount that you can change the kinetic energy by. Okay, so that's my perspective of which is the better definition, because with a work energy theorem, I think it's presented in your textbook as well. So you know that it's the same thing. It doesn't matter to me which one you write as a definition. Now, is there still any use to think about work? Yes. In fact, this is where all the other formulas, like what have we learned so far? We've learned 3 formulas. mgh is the gravitational potential energy on Earth. Half kx squared, or half k delta x squared, is the energy stored in a spring. If you compress it or extend it by some displacement, that's the energy stored in the spring. This is the gravitational potential energy on Earth, and the universal gravitational potential energy, right, stored in any gravitational attractive masses. It's minus gm over r. So where does these formula come from? It's really from this, okay? And how I like to interpret work done on something by a force, it's really the energy required for a force being applied over a certain distance. Displacement. Now, I wouldn't use this as a definition of force. I will use this, definition of work. I will use this as the definition of work, and we'll unpack what does this dot of 2 vector means. It's called a dot product or a scalar product. The full name is a scalar dot product, so you can shorten that to a scalar product or dot product. We'll unpack that and look at a special case, because in some special case, you can simplify that to just f vector dot dr, delta r, like this. And in some special case, you can simplify that even more. And this is actually equivalent to the magnitude of these times cosine theta, and we'll talk about that. And some cases it simplifies in even more. It's just f times dx, okay, like this. Okay, so this is when f is constant. This is when f is parallel to this. So in certain cases, it simplifies to an easier formula like this, or like this, but that's the most complete one. Okay, so we'll unpack a lot of what those means today. So we will look at that. And the first thing we'll look at is this dot product, right? This scalar dot product. How does that work between vectors? And then we'll look at each definition, the simplified definition, or special cases of the definition. And we will look at where these formulas come from. So calculating the energy formulas of different types of energy, right? And finally, we'll look at just some examples on how this will all relate to using energy to sort of the energy approach of calculating things. Okay, so just to reiterate, that is normally energy is defined as the ability to do work, and work is essentially defined as force times distance, right? Force times displacement, but roughly speaking like that. I would prefer energy to be defined as the ability not to do work, but the ability to change your kinetic energy. And and now I can define work. So instead of defining energy with work, I can use energy to define, instead of using work to define energy, I can use energy to define work. Okay, and that's slightly more intuitive. It's the energy required for you to push something, for a force to be applied over a certain distance. Okay, so just very roughly, right? If I apply a force over on this box of like 10 newtons over a displacement, a distance of 2 meters, how much energy is required to do this? And the answer is, if this is sort of the simplest case where my force is parallel to my displacement, right? The force is this way, the displacement is this way, and then they are also constant. So I'm applying a constant force, so I can just multiply the two together, and the answer is 20 joules. So I know I need 20 joules of energy in order to push it with this. So that is basically what work done is. But so that's easy, very easy to understand. But let's understand the more complicated version and then simplify it further as well.